So this is video number 2 for part C of number 7. So we're trying to prove that, or show that it's true that the determinant of an orthonormal set of orthonormal columns in a matrix, that the determinant would be either a positive one or a negative one. So we could take the determinant of this in general form. How would we take the determinant of this matrix? Is we'd cross multiply and then subtract this product minus this product. So we take a times d over radical a squared plus b squared times radical c squared plus d squared. So that will give us the determinant of that matrix. Let's call it the determinant of matrix A would be AD over the square root of a squared plus b squared times the square root of c squared plus d squared minus this cross product b times c, which is bc, over the same thing, radical a squared plus b squared times radical c squared plus d squared. This, when simply have the same denominator, that's just going to give us AD minus BC over the square root of, now since those are both square roots, we can just multiply that. A squared plus B squared will be multiplied by C squared plus D squared. That whole radical. So this is what we want to, show this is equal to 1. In order for this to be equal to 1, we really want to show that AD minus BC would be equivalent to the square root of this. Now it could be opposite also. They could either have, they could be positive 1 or negative 1. That's what we're trying to prove. So let's try and show that the numerator and denominator are equivalent. And if they're equivalent, or they could have opposite signs. If their signs are opposite, right? If their signs are opposite, then if you square it, both of them, then it doesn't matter if they're both one's negative and one's positive, the answer will come out to be the same. So if we square the numerator and we square the denominator, then those should be equivalent. So let's square AD minus BC. So AD minus BC, when you square that, if you FOIL that out, you get a squared d squared. And then AD times negative BC times 2, because you'll get the, again, you'll do that twice. So that's minus 2 ADBC. And then negative BC squared will be positive B squared C squared. In the denominator, we're squaring a radical, so that's just going to be whatever's inside the radical, a squared plus b squared times c squared plus d squared. So now, let's go ahead and remember, we're trying to prove if these could be either equal or opposites, then when you square them, they should be equivalent. So we want the numerator and denominator to be the same. So let's square that denominator, or let's multiply out the denominator. So the numerator is a squared d squared minus 2ADBC plus b squared c squared, all over a squared plus b squared. If you multiply this out, distribute a squared times c squared is a squared c squared. A squared times d squared, that's plus a squared d squared. Then b squared times c squared. And then b squared times d squared. Okay. Now, these look like they have some similarities. You see we have some a squared d squared and a squared d squared. So those two terms are similar, and these two terms are similar. But what we want to show is that these are all supposed to be the same. So a squared c squared plus b squared d squared would have to be equal to negative 2ADBC to show that this was equal to 1. Well, what we do get is we know since they're orthogonal, that's given, we're assuming they're orthogonal, AC plus BD equals 0, which if AC plus BD equals 0, then AC is equal to the opposite of BD. So wherever you have A times C, you can replace it with the opposite of B times D. And you can see right here we have an A and a C here. So the AC can be replaced with a negative BD. So this numerator, I'm going to come up here, this numerator is A squared D squared minus 2. There's the DB is already there. And now I'm going to replace that AC with negative BD. Oh, this is DB, not DD. DB. So the AC is replaced with negative BD. Well, that makes that a positive, and DB would make that D squared and B squared, wouldn't it? Plus, this is B squared C squared still in the numerator. So this is being replaced with really positive 2D squared B squared. Now in the denominator, notice we've got an A squared C squared. Well, AC is equal to negative BD. So A squared C squared is what you get from squaring this side. So if we square this side, we'll get a positive B squared D squared. So we can replace this A squared C squared with B squared D squared. And we already had an A squared D squared plus B squared C squared plus B squared D squared here. And these two are like terms. And that should give us A squared D squared in the numerator plus 2D squared B squared plus B squared C squared all over. Now if we combine those, we get A squared D squared here. We get B squared D squared plus BD squared. That's 2D squared B squared again. And then we get plus the B squared C squared. So we've shown then that that would be equal to 1. So the determinant of an orthonormal set is always going to have a determinant that's either positive or negative 1.